Hello everyone, myself Mrs. Prachi Kale, Assistant Professor from Department of Mechanical Engineering, VPKBIT Baramati. Today we are going to see velocity and acceleration analysis of simple mechanism using graphical method by using relative velocity method. Before starting, let us revise some basic concepts of velocity and acceleration diagram. Velocity of a link. The direction of velocity of a link is perpendicular to the link in the direction of rotation. The magnitude of velocity vector v is equal to r into omega, where r is the length of a link and omega is the angular velocity of the link. Acceleration of a link. Acceleration of a link will have two components of acceleration: centripetal acceleration and tangential acceleration. Centripetal acceleration will have magnitude v square upon r, where v is the velocity of that link and r is the length of the link, and its direction will be parallel to the link towards the center of rotation. And tangential acceleration will have magnitude ft is equal to r into alpha, where r is the length of the link and alpha is the angular acceleration of the link. The direction of tangential acceleration is perpendicular to the link in the direction of rotation. So this acceleration will be for the link which will have turning motion. Now, if the link will have linear motion, that is, if it is a slider, then velocity and acceleration of slider both are parallel to motion of the slider in the direction of motion. So we can locate only the direction of the velocity vector and acceleration vector of a slider. We can't locate its magnitude. It can be located after completion of velocity and acceleration diagram. So these are some basics of velocity and acceleration vector. Using this, now we are going to see one example to draw velocity and acceleration polygon. In the toggle mechanism shown, the slider D is constrained to move on a horizontal path. The crank OA is rotating at 180 rpm counterclockwise, increasing at a rate of 50 radian per second square. The dimensions of links are OA equal to 180 mm, CB equal to 240 mm, AB equal to 360 mm, BD equal to 540 mm. For the given configuration, find velocity of slider D, angular velocities of link AB, CB and BD, angular acceleration of BD. In our previous videos, which we have seen for velocity and acceleration diagram, crank was rotating with constant velocity, angular velocity. Now, this is the case where crank is rotating with a uniform acceleration of 50 radian per second square. So velocity is not constant, but it is having alpha having value of 50 radian per second square. So now we will see how to draw velocity and acceleration diagram in case crank is not rotating with uniform velocity, but it is having a acceleration. Solution. Step number 1. To draw configuration diagram by assuming some suitable scale. So first we have to assume certain suitable scale to draw the configuration diagram. So depending upon the given dimensions, we will assume a scale equal to 1 cm equal to 60 mm. So how to decide this scale? So depending upon these dimensions given and the space available on our sketchbook or drawing sheet, we have to choose the scale. The scale should be such that the configuration diagram is properly visible. So here I have taken the scale 1 cm equal to 60 mm. So while drawing the configuration diagram, I will convert all these dimensions as per our scale. Say for example, for OA, I will take 3 cm. For CB, I will take 4 cm. For AB, I will take 6 cm. So I have to convert all these dimensions as per our scale. Now we have to draw the configuration diagram. So I will tell you what will be the procedure to draw the configuration diagram. So first take point O as a reference point. From O, draw a horizontal line of 360 mm offset. So convert this 360 mm as per the scale, that is it will be 6 cm. Draw a horizontal line and a vertical offset of 105 mm. Where these two will intersect, you will get C point. So now we got O point and C point. Now from O, draw angle of 45 degree, and on that line at 45 degree, take distance equal to OA. So here OA is given 180 mm. So here we will take 3 cm for OA. Now we got A point. Now take compass and take distance equal to AB in a compass. So AB is given 360 mm. So convert it into scale 6 cm. Take distance 6 cm in a compass, and from A draw a arc. Then from C draw a arc of distance equal to BC, that is 240 mm. Where these two arcs will intersect, you will get point B. Now once we get point B, take distance in a compass equal to BD. So BD given 540 mm, convert it into scale, and with that distance of BD, make an arc cutting this horizontal line from B. So in that case, we will get point D. So that is a sliding. So like this, complete the configuration diagram. Remember, there are no any marks for the configuration diagram in the marking system. But if the configuration diagram is wrong, entire velocity and acceleration polygon will go wrong. So it is required to draw the configuration diagram very neatly and very carefully without any mistake. Now step number 2, to calculate velocity of input link. So always in a question, velocity of input link will be given in terms of either RPM or in terms of angular velocity radian per second. So in this case, it is given n equal to 180 RPM. From this, we will calculate omega equal to 2 pi n by 60. So substitute n equal to 180 in this formula. We will get omega equal to 2 pi n by 60 equal to 18.849 radian per second. Now using this omega, we have to find linear velocity, that is v equal to r into omega, where r is the length of the link and omega is the angular velocity of the link. Now here, while substituting OA, we need to take the actual length of the link given in a question. Do not take the dimension which we have used to draw the configuration diagram. We have to use the actual dimension of OA. So it is given 180 mm. So we have taken it into meters so that we will get linear velocity in meter per second. So after calculating this, we will get it as 3.392 meter per second. Now using this value, we have to take a suitable scale to draw the velocity polygon. So again, you have to decide the scale such that this value should be properly drawn. So here I have taken 1 centimeter equal to 0.5 meter per second. With this scale, we can draw the velocity diagram. Remember, there is no any relation of scale of configuration diagram and scale of velocity polygon and scale of acceleration diagram. We can take all the scales differently as per the values. Now here, with this scale, we have to go for velocity polygon. Now step number 3, to draw velocity polygon. So this is the configuration diagram with which we have drawn 0.5 meter per second scale. With this as a reference, we have to draw the velocity polygon. One more thing I would like to tell you is that in a sketchbook or on your page, you can draw configuration diagram, velocity polygon and acceleration polygon at any locations. Only the thing is that they should all must be on a single page because we have to draw the lines parallel and perpendicular to the links in the configuration diagram. There is no any rule that where should be the velocity polygon and where should be the acceleration polygon. It can be drawn anywhere aside of the configuration diagram. Now let us start with the velocity polygon first. And one more thing is that to draw the acceleration polygon, always we need to draw the velocity polygon first. Without drawing velocity polygon, we can't proceed for the acceleration polygon. Now we have to start with the reference point. So this is the reference point. The names to the reference point are whatever the fixed link in the mechanism, they have to be given at a single point. So here O is a fixed point and C is a fixed point. So this is a point O and C at a same location. How many number of fixed points in a configuration diagram? All have to be drawn at a same location while drawing with the velocity polygon. With this point, we will start the velocity polygon. Now first we have to draw velocity vector for crank. So this is a crank. Always we will start with the crank. So crank OA is rotating in an anti-clockwise sense. So velocity vector of a crank OA is perpendicular to OA in upward direction. Why upward direction? Because this is rotating in an anti-clockwise sense. Velocity vector is perpendicular to the link in the direction of rotation. So this is the direction of rotation. So it will be perpendicular in upward direction. So from O perpendicular to OA in upward direction will be the velocity vector. See, remember, don't say it is that towards O. It should be in the direction of rotation. So I will say it from O in a upward direction. Don't draw it over here. Okay. So this is the velocity vector perpendicular to OA. Now the length of this velocity vector is equal to whatever the linear velocity we have found previously, convert it into the scale, and with that dimension we have to draw this length of velocity vector. We have got something 3.3 meter per second. So convert it into scale, that is multiplied by 2 we need to do. Then whatever the distance you are getting, 6.6 centimeter approximately, that you have to take it for this velocity vector. So while drawing velocity polygon, we have the value of velocity of only the crank. The magnitude will be known only for the crank. For rest of the other links, we will not have the magnitude of the velocities. Only we will have the directions. So they have to be located using the intersection of velocity vectors. Now we have got this point A, and this is the velocity vector for OA. Now we have come up to A. Now we have to go to link AB. So velocity vector of AB will be from A. It should be drawn from point A perpendicular to AB. So perpendicular to AB from A, this is the velocity vector of AB. So here we don't know what is the magnitude. So just draw a line from A perpendicular to AB. Now here you might have questioned that why to draw in this direction and why not to be drawn in this direction. So you can draw just a line and keep it as it is. Actually, when this will rotate in the anti-clockwise sense, the AB will rotate in towards right. So that's why this velocity vector is towards right. But if in case it is not possible for you to locate what should be the direction of velocity vector of any link, just draw a line. So you can draw a line here. Okay. So it is not required that you should be known that what should be the direction. So just draw a line and keep it as it is. Whenever the point will intersect, that will give you the actual direction. So we don't know the magnitude as well. So keep this vector as it is. Keep this vector as it is. Now as point B is on this link AB, it is also on link CB. It means that B point should be on the velocity vector of AB. So this is the velocity vector of AB. somewhere on this line there should be a B point, and that AB will be velocity vector of AB. But at the same time, point B must be on the velocity vector of BC also. So we will draw the velocity vector of BC now. So velocity vector of BC will start from C and perpendicular to BC. So from C perpendicular to BC, this is the velocity vector for BC, or you can say CB. And where these two vectors will intersect, it will give you point B. Okay, because link AB and CB intersect at point B. So velocity vector of AB and velocity vector of BC intersect at point B. So like this we have to locate point D. Now after coming up to point B, now we will go to link BD. So velocity vector of BD will be perpendicular to BD from B. So from point B perpendicular to BD, we will draw a vector which is velocity vector of BD. So this is a velocity vector for BD. On this line there will be point D. But as D is on BD, it is also slider. So it will be at the intersection of velocity of slider and velocity of link BD. So velocity of slider will be parallel to motion of the slider. So slider is moving horizontal. So we will draw a line horizontal from a point on which slider is moving. So slider is moving on a fixed point. So from fixed point we will draw a horizontal line. So this is velocity vector of slider, and the intersection of these two will give you point D. So this is velocity vector of BD and this is velocity vector for slider D. So in this way, by the intersection of velocity vectors of all the links, we can complete the velocity polygon. Now it is asked to find velocity of slider D. So velocity of slider D is equal to velocity of vector D, that is this OD. So measure this distance OD, multiplied by scale, it will give you this answer as 2.2 meter per second. That is velocity of slider. Similarly, we can find velocity of link AB. So velocity of link AB, measure this vector AB, length of this A to B point. This distance into scale will give you velocity of AB, that is 0.75 meter per second. Similarly, we can get velocity of point BC or vector BC. So measure this distance BC, actual distance over here in this velocity polygon, multiplied by scale, it will give you 2.85 meter per second. Similarly, for velocity vector DB, measure this distance DB, multiplied by scale, it will give you the velocity of DB as 2.4 meter per second. Like this, we can find linear velocities of any link from this velocity polygon. Now it is asked to find angular velocity of AB, that is omega AB. So we know V is equal to R into omega, or omega is equal to V divided by R, that is length of the link. So measure this velocity of AB divided by actual length of AB. Now remember, this should be the dimension which is given in an example. Do not take with which you have drawn the configuration diagram. Don't take the scaled value. Take the actual dimension, so that you will get the actual velocity of the link AB. And then you will get actual angular velocity of link AB as 2.083 radian per second. Similarly, we can find angular velocity of BC equal to omega BC equal to velocity of BC, which we have found out earlier, divided by length of BC, that is the actual length of the link. After calculating, it will give you value as 11.875 radian per second. And similarly, we can get angular velocity of link BD equal to omega of BD equal to velocity of BD divided by length of BD equal to 4.44 radian per second. Remember, these values will change as per your scale. There is a variation possible due to the graphical error and the different scale. So 0.2 meter per second variation plus minus 0.2 meter per second variation is allowed. You will not get exactly these values because as per the individual's graphical error, there can be some little bit change in these values. So this is the procedure to draw velocity polygon. Now step number 4, to calculate the magnitudes of acceleration. So for this we need to prepare this table in which all the lengths of the links, the velocities of the links, the centripetal acceleration and tangential acceleration need to be calculated. So length of link OA given 0.18 meter, measure the velocity of this 3.392 which we have calculated already. Then find out the centripetal acceleration equal to v square by r. So 3.392 square divided by 0.18, that is the centripetal acceleration. And its tangential acceleration is equal to r into alpha, where alpha is given in the question and r is the length of the link. After calculating this, it is giving 9. That is the tangential acceleration in meter per second square. And the direction of tangential acceleration is perpendicular to the link. See, for this case, alpha is given. That's why crank will have centripetal as well as tangential acceleration. If alpha is not given, then this will be equal to 0. In that case, crank will have only centripetal acceleration. But for the other links, AB, BC and BD, it will have centripetal acceleration and tangential acceleration both. Only the magnitude is unknown, but the acceleration component need to be located. And for slider, there will be have 0 value of centripetal acceleration as slider will have linear motion. So its magnitude will be unknown and its direction will be parallel to motion of the slider. So using this data, we have to calculate the centripetal components of acceleration for all the links AB, BC, BD. It is calculated by using v square divided by r. V square divided by r, that is velocity square divided by length of link. So we will be getting the magnitudes of all the centripetal components of acceleration. Now this table is required to draw the acceleration polygon. After this, we have to assume the suitable scale to draw the acceleration polygon. So step number 5 is to draw the acceleration polygon. So depending upon whatever the values we have got, we have to take a scale. Now this is the configuration diagram which we have drawn it earlier. Now again we have to start with a point and we will give name as O and C, that is fixed point. Now always we will start with the centripetal acceleration of a link and then tangential acceleration and then total acceleration, and we have to start with the crank always. So first we will locate centripetal acceleration of crank OA. So centripetal acceleration of crank is parallel to OA towards the center of rotation. So O is the center of rotation for link OA. So centripetal acceleration will be towards O, means downward. So once you say downward, then from O draw a line parallel to OA, vector parallel to OA, and of magnitude equal to the centripetal acceleration which we have calculated in the table. Remember, don't get confused for the direction. As I say it is towards O, it doesn't mean that you will draw it over here, that arrow towards O. Once you say towards O means downward. So remember this point, downward. Remember this word, downward. Towards O means downward. So from O in a downward direction parallel to OA is the centripetal component of acceleration for link OA. Now where the centripetal component end, that is at A dash, you have to draw tangential component. Now tangential component is perpendicular to the link. So perpendicular to OA. Now from A dash, you have to draw perpendicular to OA. Now it can be upward, it can be drawn downward. A perpendicular line can be drawn upward also, perpendicular line can be drawn in a downward also. But it should be in the direction of rotation. So just see over here, what is the direction of rotation? Anti-clockwise. So it is moving anti-clockwise. So the perpendicular will be upward. Anti-clockwise direction is moving the link in a upward direction. So tangential component will be in a upward direction. So from A dash, we will draw a line or a vector which is perpendicular to OA in a upward direction, not in a downward direction. So this is the direction, and the magnitude is what we have calculated in the table. Convert that value of tangential component into the scale, and with that dimension draw the tangential component of this link OA. So this is a tangential component, and the resultant, so join this triangle, it will give you the resultant of OA. So for every link there will be three components of acceleration, three vectors of acceleration: centripetal component, tangential component, and total acceleration. Then we come up to A. Now we have to go for AB. So always we have to draw centripetal acceleration of AB first, then tangential acceleration of AB. So centripetal acceleration of AB we have to draw from point A. So this is the final point A. From here we have to start with the centripetal acceleration of AB. So centripetal acceleration of AB is parallel to AB towards the center of rotation. Now A is the center of rotation for AB. When I say link AB, A is the center of rotation. If I say link BA, then B is the center of rotation. So how to consider the names? So in the sequence which the motion is transmitting, like how is the sequence? OA, then AB. So that's why A is the center of rotation. So centripetal component will be towards A. So when I say towards A, it means upward. So from A parallel to AB in upward direction is the centripetal component. Will not draw in a downward direction, because if you will draw it in a downward direction, it seems as a towards B. But it should be towards A. Towards A means upward. The motion for towards A should be drawn upward. So this is the centripetal component of AB. At the end of centripetal component, from this point, that I will give name as B1, because there will be number of B points. So I will say it as a B1. So at the end of B1 you have to go for tangential component. So tangential component will be perpendicular to this centripetal component or perpendicular to AB. Now here tangential component can be drawn here also. It can be drawn over here also. But at same which we have seen, the velocity of AB is towards right. The tangential component will be also towards right. Or if it is not possible to you to decide whether to draw tangential component in this direction or whether to draw tangential component in this direction, simply you can draw a line. Just draw a line, rough line. We will finalize afterwards when you will get the intersection. Okay? No queries if it is not possible to you to determine the direction. Simply draw a line which is perpendicular to AB. Now we have to keep it as it is, because we don't know what is the magnitude of the tangential component. So keep this as it is. Now as AB is the link for which we have drawn centripetal and tangential component, and B is on the link AB, it is also on the link CB. It is at the intersection of CB and AB, B point. So as B lies on the acceleration vector of AB, B must lie on the acceleration vector of CB also. So keep this as it is now, and let us move towards CB, link CB. So for link CB, first we will draw centripetal component of CB. Now centripetal component of CB or BC. See, actually I should call it as a BC, because in the sequence it is as BC. But centripetal component of a link, if its one point is fixed, then it is always towards the fixed point. So in this case, C point is fixed. So component of CB or BC must be towards C. Okay. If any one point of a link is fixed, then its centripetal component must be towards that fixed point. That fixed point will be its center of rotation. So here center of rotation is C. So centripetal component will be towards C. It means downward. So from C point in a downward direction parallel to BC, we will look at centripetal component of BC. So its magnitude, take it from the table which we have calculated already. Convert that magnitude into the scale. Okay. And that will be the centripetal component's magnitude. So this is the point B2 and this is the centripetal component of BC. Now where the centripetal component ends, we have to draw its tangential component. So this tangential component is perpendicular to BC. So here also, if you don't understood whether to draw in a downward or upward direction, simply draw a line. Okay, just draw a line over here which is perpendicular to this centripetal component. Now this line which is perpendicular to BC and this line which is perpendicular to AB will intersect at a common point, that is your final point B. Now if in case you have drawn it a line over here and this line over here, these two lines will not intersect. It means that it should be drawn in this direction only. So this is the total final point B. And if you complete this triangle, then this is the total acceleration of link AB. Centripetal of AB, tangential of AB and total of AB. Same way if you complete this triangle, this is centripetal of BC, tangential of BC and total acceleration of BC. And B is at the intersection of these two total components. Now we came up to point B. Now from B, we have to go for link BD. So from this point B, first we will look at centripetal component of BD. So centripetal component of BD will be parallel to BD towards B. Now center of rotation will be B, as I am saying link BD. So B means in this direction. So from B in this direction parallel to BD is the centripetal component. The magnitude you have to take it from the table. Centripetal component of BD. The magnitude of the centripetal component, convert it into scale and take that distance on this vector. So this is centripetal component of BD. Now perpendicular to this is the tangential component of BD. So just draw a line perpendicular to this centripetal component. This is the tangential of BD. Now we don't know what is the magnitude of the tangential component. So keep that vector as it is. Okay. Now we will go for slider, because as D is on link BD, it is also on slider D. So D must be at the intersection of tangential of BD also and this slider also. So how will be the acceleration of slider? Acceleration of slider will be horizontal, linear. So from O in a horizontal direction, just draw a line. That is the acceleration of the slider. And where these two intersects, it gives point D. So this is the acceleration of slider. This is the acceleration, tangential acceleration of BD, centripetal acceleration of BD. And if you complete this triangle, this is the total acceleration of BD. So in this way, we can complete the acceleration polygon. Now it is asked to find acceleration of slider D. So measure this distance, multiplied by scale, it will give you acceleration of slider D. Vector OD you have to measure, multiplied by scale, it will give you acceleration of slider D. Then it is asked angular acceleration of link BD, that is alpha. So to find out angular acceleration of BD, we know the relation between angular acceleration and the tangential acceleration. That is Ft is equal to BD into alpha BD. Ft equal to R into alpha. Out of this we can find out Ft, directly measure the vector BD, tangential component, multiplied by scale, it will give you Ft of BD as 35.95 meter per second square. And BD is given 0.54 meter. Substitute these two values in this formula. It will give you alpha of BD equal to 66.574 radian per second square. So in this way, you can calculate angular acceleration of any link. Now again, whatever the answers you are getting, you may not get exactly this value because of the graphical error, or if in case you have taken some different scale. So 0.2 plus minus meter per second square variation is allowed. You will not get these values as same as it is. There may be variation which is accepted. So this is because of the error, as this is a graphical method. Error while drawing the parallel and perpendicular line, and also if you are taking some different scale, then also there can be error because of the scaling factor. So like this you have to draw the acceleration polygon, and with this acceleration polygon you can find out acceleration of any link, tangential acceleration and angular acceleration of any of the link. Thank you.